Hi, welcome to Module 5 of Lecture 11. This is the second of 4 modules looking at how to solve systems of linear equations. In the previous module, we did substitution, sort of the go-to method. It's going to work, it's going to produce an answer, and you don't have to remember anything to do it. However, it's oftentimes related to a lot of unnecessary algebra. Now we're going to do a pretty closely related technique, actually, called elimination. Now there are many varieties of elimination. We're just going to go through and give the basic idea, the basic notion. Actually, it turns out to be pretty similar to both substitution and also to the thing we've been talking about so far, which is what if I add two equations together? Turns out the goal of elimination is to produce a system of equations that look kind of upper triangular. So you want to produce, so if you have, say, 3 variables, you want to look like this. Let's see, D, and then you want this to be and then you want, right? So basically upper triangular, again, the variable names don't matter. The point is, which you solve for first doesn't matter. The point is you want to end up with this kind of equation. Then what you do is you first solve for z, then it's called back substitution, which is no different than any other kind of substitution, mind you. You take z and you plug it in here, then you solve for y. You take y and z and plug into here and solve for x. So honestly, it's very similar to substitution in a lot of ways. Just the goal is the goal is to systematically create these kind of equations to make your life easier. If you do it well, they can be faster than substitution because you're not going around. You're doing a better job finding the simple equations first and not having to go through and do a whole bunch of manipulation and a whole bunch of algebra that you do for substitution, because now you can sort of do things faster, more efficiently if you are practicing elimination. And there are also other varieties of elimination where you create matrices and things that help you keep track of everything. But again, in all cases, the major point is this. You create a system of equations in which you have one equation for one variable, another equation for 2 variables, including that one, then for 3, including those 2, and so on. And then once you solve that, you solve the smallest one first, and you back substitute up to get the solution for all of them. So again, we'll do an example of this to see how this works. But before we do that, how do you get these equations? You get these equations by operating on equations themselves. And there are 2 kinds of operations you might care about. One is you can multiply any equation by any constant. Let's consider left-hand side and right-hand side. Right, so you have an equation 1, which is left-hand side of equation 1 equals right-hand side of equation 1. That could be left-hand side, right-hand side, or anything else you want. Well, if I multiply both sides by 2, that equation should still hold. If a equals b, then 2a must also equal 2b. That's what it means to be equal. So I can multiply any equation I want by any other equation I want. So that includes negative numbers. So I can have negative 1 left-hand side equals negative 1 right-hand side. Second, I can add or subtract, in this case, if I multiply by a negative number first, I can add or subtract any equations I want. So for instance, if left-hand side of equation 1 equals the right-hand side of equation 1, and if the left-hand side of equation 2 also equals the right-hand side of equation 2, I can say also, then left-hand side of equation 1 plus left-hand side of equation 2 has to equal right-hand side of equation 1 plus right-hand side of equation 2, just because this equals this and this equals this. The same thing would be true for subtraction. And in fact, the same thing is true for multiplication and addition. So for instance, if I have a constant a over here and then a constant b over here, even if b is negative, that also works just fine. In a nutshell, I can take any linear combination, because that's what these are linear combinations, not by accident. I can take any linear combination of any series of equations and then produce a new equation that must also be true. And the goal of elimination is to operate directly on equations and produce a system of equations that looks like this, so I can easily substitute. That's the goal. So let's do an example. Again, we'll start with 3 equations. Just go right to 3 equations, and we will do that by again writing the answer down first. Let's try this as a default answer, because why not? And let's start making up numbers. And okay, so the first one is 2 plus 2 is 4, minus 9 is -5. The second one is 1 minus 2 is -1, plus 6 is 5. And the third one is 3 plus 4 is 7, minus 3 is 4. So there you go, 3 equations and 3 unknowns. We're going to try to solve this thing using elimination. Now, the trick to elimination is not trying to solve one equation for a single variable, like in substitution, but rather trying to see if you can add or subtract multiples of different equations together to eliminate variables in both equations. So how do we do that? Well, to eliminate variables, rather. So how do we do that? Let's see. If we add 1 and... So let's number the equations. It helps to do that. If we add 1 and 2 together, we get rid of y. So now we have 1 prime, we'll call it. And that's going to be 3x. We're adding the left-hand sides together, plus no y, minus z. And the right-hand sides together, -5 plus 5 is 0. So now we have a nice simple equation with no y in it. Okay? And now we want 2 prime. We need to also get rid of y again. So, but we can't use the same 2 equations, obviously. We need to use different equations. So let's now take 2 times equation 2 and add it to equation 3. So 2 prime is formed from 2 times equation 2 plus 1 time equation 3. Well, we have 2x plus 3x is 5x. Negative 2y plus 2y is 0. 2 times 2 is 4z. Minus z is plus 3z. And then 2 times 5 is 10. Plus 4 is 14. So that gives us 14. So we have 14 over here, and there's 2 equations and 2 unknowns. And that gives us, we can choose from either of these 2 things to be our equation for our next stage equation. Okay? Now finally, we need one more equation that has only 1 variable in it. Well, what if we add 3 times equation 1 prime plus equation 2 prime? That should cancel the z's. So we'll do that. 3 times 3x is 9x plus 5x is 14x. So here's our equation 1 double prime is 14x. Negative 3z plus 3z is 0. 3 times 0 is 0, plus 14 is 14. And there's our last equation. So what we've done now is by adding and subtracting multiples of equations, we've gotten to the point where we have equations we can use. So first, now we solved the last one we have, the bottom one, is 1 variable, so x equals 1. We can now use either of these 2 equations as our next level equation to plug back into. So 1 times the first one is 3. So plug in 1 over here, you get 3 minus z equals 0, or z equals 3. And again, I could have done this equation too. 1 times 5 is 5. It's 3z equals 9, or z equals 3. They both give the same answer. Now I plug back into the previous one, and we discover, and we pick anyone we want to pick, because we use all of them. So let's pick 2, because that's simplest. 1 plus 6, 2 times 3 is 6, so it's 7 minus y equals 5, or y equals 2. And we're done. So this is elimination. I should say this is a very inefficient use of elimination. We've actually went through and have produced multiple equations that we can use to solve things with. You don't, by and large, need to have this many equations. You can be more efficient in the process. However, the reason I did it this way, A, I'm doing it on the fly, so it's a good way to see how it works no matter what, and B, it gives you more practice in manipulating, adding and subtracting equations. So that's why I did it this way. And again, there's more examples in the book, and there are a lot of other more specific ways of doing elimination, Gaussian elimination, and so on, that you can use and become more efficient at if you like this kind of style of equation solving. Okay. I want to really quick give one more example that's not going to work out so well. What happens if we had an underdetermined system? Right, I can use the simple example from before. 6 and x plus 2y equals 3. So we know that the first one is twice the second one. How would this work using elimination? Well, let's say we want to eliminate x from the equations. I can multiply, so I have 1 plus, minus 2 times equation 2. Well, that would give me 2x minus 2x is 0, great. But 4y minus 4y is also 0. Not as good. And then 6 minus 2 times 3 is 6. So we get the wonderful equation that 0 plus 0 equals 0. Not very helpful at all. If we had 3 equations with 3 unknowns, of which 2 of the equations were unique, we would again produce, somewhere in the process of doing elimination, the same kind of thing like this. Right? But frankly, I find substitution a little more helpful in this particular case than elimination. But you can still do this. This is not this case, by the way. This is just a different example. You can still do this using elimination for undetermined systems. And for overdetermined systems, again, you could do this and show that there's a contradiction somewhere in your equations. And the book has examples of those two things. Having already done that in the previous module, there's no real point to repeating examples that do the exact same thing as before. The important thing to note is if it's an overdetermined system, you have a contradiction. If it's an underdetermined system, then you will have some kind of space of solutions that's more than just a single point. And you have to solve for one variable in terms of one or more other variables. That's it for elimination. The next one we're going to go on with is matrix inversion. Thank you very much.